And if you take the objects around you and you apply the right kind of math to them, you can predict them with extreme accuracy, and everything around you works like this magnificent clockwork, and everything is connected in this cause and effect comprehensible way. That was a massive paradigm shift in society, and it affected.
Yeah, I see.
It's modernism. Modernism has massively influenced society. It's built the buildings around us, and now there's this new kind of physics. So its effects are in their infancy compared to the effects of Newtonian physics, but they're already having a massive impact on the way people think, on the way people choose to live their lives. You are tuning in to the Multiversity, a podcast for higher dimensional education.
Join us as we explore philosophy, science, history, and the great unknown.
Hi, everyone, and welcome to the Multiversity. I'm Arielle, and I'm going to be facilitating this amazing conversation about quantum physics. Chris, Katie, do you guys want to introduce yourselves?
Hello, my name is Katie. I have never taken a physics course before, but I'm excited about this.
Hello, I'm Chris, and I talked about physics and philosophy a lot in college.
Thanks, guys. So today we have a very special episode. We're going to be talking about quantum physics and what this mysterious science tells us about reality. We'll start by looking at some notable experiments in quantum physics, starting with the double-slit experiment, and then moving on to different interpretations, like the Copenhagen Interpretation, the many worlds interpretation, and others, and try to bring these interpretations into everyday philosophy and how we should understand reality. So today we have John Long joining us as guest star. John, why don't you introduce yourself and tell us a bit about your background to start?
Hey, I'm John. Let's see, I have a BS in physics and a PhD in computer science, and I currently work in the field of robotics.
Very cool. We like robots on this show.
Yes, we do. Taking all the jobs.
Usher in the robot utopia. Anyway, not what we're talking about today. Today we're talking about physics. So to start our conversation, we're going to be talking about the double-slit experiment. So John, do you want to maybe give us a brief intro to this important experiment in the history of physics?
Sure. So the double-slit experiment really gets at one of the key things which originated with the theory of quantum mechanics, which is this wave-particle duality of matter. Basically, the way this is set up is you have some kind of screen which has two slits in it. That's why it's called double-slit experiment, of course. And now we know from classical physics that when a wave propagates and it passes through a small hole, the wave will spread out from that hole in a process which is sometimes called diffraction, but all that means is that the wave reaches a hole, it's then restricted so that the only place it can come from on the other side of this barrier is through the hole, and the wave spreads out. And now if you have multiple holes which are near each other, you'll get multiple points where the wave spreads out, and you can essentially think of that as two new sources for two new waves. And because these are waves, they can interfere.
So just to break it down a bit, the basic elements from what I can see in this experiment are you have like a wave, or this idea of a wave. So in a wave, if you have two waves interfering, then you'll see if you put a two-dimensional screen against them, waves or a series of bars. And some bars represent where the high point of the waves are matching, and some bars represent where the low parts of the waves are matching. And that's what you mean by interference between the waves, right?
That's right. You have some peaks and some troughs where the waves either interfere constructively or interfere destructively.
And we see this with water waves. It's a classical phenomenon. And by classical phenomenon, we mean a phenomenon that can be explained using the Newtonian physics, like the physics of the objects in the worlds that we exist in, balls rolling down hills, waves in the water, stuff like that, right?
Correct. In other words, pre-quantum physics.
Right. One way to imagine this is like when you have, or at least my understanding is like if you drop stones in water at two different points and you get those ripple effects, those waves moving in the water, where those two ripples meet, you'll kind of see an interference pattern in this effect that we're talking about.
Precisely. Mm-hmm.
But you wouldn't expect that if you were dropping, say, individual grains of sand through two slits. You wouldn't expect to see them, like if you're dropping them one by one, you would expect to see them pile up. You wouldn't expect to see each individual drop to somehow create this ripple effect when they were going through one at a time. But that's what we see at the quantum level.
Well, it's interesting. So there's these two kinds of classical phenomenon. Like there's waves that are interfering, and there's particles that are just building up in a pile, like Katie described. And so the interesting thing about the double slit experiment is light seems to behave in both ways. And John, you were just describing a situation where there's one circumstance that seems really strange, is that when you shine light through at a very low intensity, so that only one photon is going through this each slit at a time, it seems to interfere with itself, which is in some way some kind of weird mashup of wave behavior and particle behavior.
Indeed, and it's not that you can pass one photon through this experiment and see the interference pattern right away. It's a statistical kind of thing where you see one dot appear on your detector, and then you have to wait and see what pattern builds up as more dots appear on your detector. And the interesting thing is that the pattern that builds up is the interference pattern.
Okay.
So it's like each electron knows what the other electrons are doing so that it can know what kind of interference pattern to draw.
In a sense, or perhaps, another way to think about this is that each particle, in some sense, has to be passing through both slits at once. I should clarify that Chris is talking about electrons now. Previously, we've talked about photons.
Right, sorry, photons.
This works, Chris is not wrong. This works with electrons, it works with photons, it works with any kind of particle. Electrons, are classically conceived of as particles, whereas, light has been classically conceived in many ways, but as a wave is one of those ways.
Yeah, the important point is whether it's a photon or an electron or whatever kind of particle you're working with. If it's a particle, if we're talking about things at quantum scale, it works in this way, right?
Right. According to the laws of quantum mechanics, there are no things other than quantum things.
It could be a collection of objects too, right? Like it could be a macroscopic object.
It could be.
What?
But the interference pattern would just be, much more complicated or something.
Well, what happens is so one of the details that I've left out is that there's a wavelength associated with all of these kinds of particles. And as the particle gets larger, in the sense of mass, the wavelength gets smaller. And so in order to see interference, the slits have to be, the distance between them has to be on the order of the wavelength. So that becomes harder and harder as things become more massive.
So how would that work? Like if the distance between the slits, like if I was the particle in the double slit experiment, I have a much larger mass than a photon or an electron, but I'm also probably too big to fit through two slits that are like infinitesimally close together. So would that just mean the experiment couldn't be conducted on like a macroscopic object?
Depending on where you draw the boundary of being macroscopic, yes, the experiment essentially could not be conducted.
Is that just for practical reasons, or is there like a physical metaphysical reason?
I think for the purpose of the basic laws of quantum mechanics, it's just for practical reasons. Now, if we want to get deeper into physics, there may be fundamental reasons why there's limitation in the length scales on which things can be constructed, even fundamentally, because there's something called the Planck length, which is a sort of theoretical boundary on the smallest length scale that makes sense to talk about. But we have to go beyond the basic rules of quantum mechanics to get there.
Like if I shot Ariel out of a cannon, to two like doorway sized slits, that wouldn't be useful, right?
That wouldn't be useful because those two doorways would have to be at least the size of one doorway apart. And that's much, much, much larger than the corresponding wavelength.
I see. So the corresponding wavelength would be something tiny.
What if the two doors were big enough to fit me, but the space between the doors was like really, really tiny, like microscopic?
Let's see. I mean, that clearly still would not work because that's an experiment we can actually conduct. So if the slits are large enough, I mean, I think there's a sort of separate but related technical aspect of this, which is that if the slits are large enough, then they're not really slits anymore.
Right. So the slits
that's
themselves,
again related to the wavelength.
so the absolute size of the slits actually matters.
The size of the slits relative to the wavelength of the particle with which you're using to conduct the experiment matters.
Gotcha. And so Ariel's wavelength would be
first place.
Ariel's wavelength would be extraordinarily tiny, right?
Extraordinarily tiny, yes. So it's inversely, hopefully I get this right, it goes inversely with the momentum of the particle, and it's also related to Planck's constant, which is very small.
Okay, so if the doorway was nearly, I'm sorry, I'm just trying to understand this. If the doorway was nearly exactly the size of Ariel and we were shooting her extremely precisely, so that like the space between like the boundary of Ariel and like the edge of the doorway was shorter than the wavelength of Ariel, and the space between the two doorways was shorter than the wavelength, could it work?
According to the basic laws of quantum mechanics, yes, you can compute some wavelength for any object, could be a macroscopic object. And if you can set things up such that the slits have a size which is on the order of that wavelength and the distance between them is on the order of that wavelength, then you can create interference. In this case, those numbers are just absurdly small.
This is so interesting. Like I never thought of like this version of the double slit experiment using like macro objects, but it seems like the result might be that basically Ariel interferes with herself and passes through the barrier.
I guess we know what we're doing next episode.
Stay tuned.
I just, before we move on for I just have one more question. Is that like that hypothetical with macroscopic objects, is that something that's known and has been proven experimentally with like smaller macroscopic objects, or is that just what we would expect based on the predictions that quantum physics makes?
Yeah, I think the answer is that it's somewhere in between. I can't speak to concretely, not being an experimental physicist, but it's certainly the case that people are interested in, in order to test the boundaries of the laws of quantum mechanics, people are interested in observing quantum phenomena at larger and larger scales of length and mass and so forth. So you certainly hear about experiments done with so-called macroscopic quantum objects, which are usually, as far as I know, just like molecules that are,
But it does seem
much bigger than a fundamental particle, but much smaller than a person.
It does seem to be useful to me to think about what would happen on the macroscopic level, because that's how our brains understand reality, and that's the reason why our brains have, in the general population, are in general, people have such a hard time visualizing what's happening on the quantum level because it's so different from what we're used to. Yes,
perhaps so, though. I mean, it is different than what we're used to because our intuitions come from that macroscopic experience of the world around us. So at some point, it may be good to let go of those intuitions.
And it seems like I was reading in preparation for this a bit. It seems like quantum physicists have been able to glean quantum effects from like a metal paddle. Like they did something where they supercooled it and they were able to put it into some kind of superposition. And that's like a very normal sized object. You can put it in the description. Like, you just Google like metal paddle quantum.
Yeah, I mean, so the, I guess this is jumping the gun a little bit, but the many worlds interpretation talks about the universal wave function, right? I mean, basically any object or a group of objects can be taken together as a quantum system, right? And it has this wave function that describes its quantum state, right?
Sure. I mean, maybe that's jumping the gun a lot, but yes, I mean, part of the point of testing the limits of the scale at which quantum phenomena occur is to see, you know, if there's some fundamental limitation to that. There are certainly interpretations of quantum mechanics or people who are uncomfortable with quantum mechanics and either think that or would be more comfortable thinking that these quantum phenomena disappear at some point and can't really describe the macroscopic world. And so far, there's no evidence that that's the case.
That quantum phenomena don't affect the macroscopic world, or that they do?
There's no evidence that they do not. All of these, every experiment that we've been able to do so far has agreed with quantum mechanics.
So maybe we should back up a little bit to kind of the implications of the double slit experiment, because we kind of went through it and we pointed out something that's weird, namely that these particles, even when you send them through one at a time, create an interference pattern as if they were passing through two slits at once, or as if they somehow were, I don't know, coordinated and were interfering with each other somehow in the background, or there's different ways that you could interpret it. But that's really strange and has a lot of implications for our philosophy and we think about how we think about the world and how things work, right?
Indeed. Yep. And that's only the sort of first strange thing that happens in the double slit experiment. And we should probably bring up the second strange thing that happens, which is that when you see the first strange thing happen, you say, well, this doesn't make any sense. I would like to detect which slit the particle is actually going through, because, well, it must be going through one or the other. And then the second interesting thing that happens is when you place a detector that tells you which slit the particle is going through, how would you do this? Well, in the case of an electron, let's say, you could have a light source which would interact with the electron and create some kind of light that you would see, either coming from one slit or the other. So what happens when you do that is that you get a readout saying, okay, the first time the particle went through the left slit, then it went through the right slit, then it went through the right slit again. Everything seems like it's making sense, but then you look at the pattern that's building up on your detector screen, and what you see is that the interference pattern is no longer there.
Dun, dun, dun.
So in other words, when you set up some kind of detector to be able to tell with precision which slit the photon or electron or whatever you're using pass through, then the photons no longer behave like waves. They behave like particles, like Katie described before, that are just like particles of sand. They're just falling through one slit or the other. There's no more interference pattern.
Yeah, so basically the act of putting the detector there and measuring the particles as they go through the slits changes the behavior of the particles.
Well, that's an assumption. We don't know that it's actually the act of measurement that changed the behavior of the particles.
Well, what I'm saying is there's a difference between the two versions of the experiment, the one without the detector and the one with the detector, and they have different results. And so we can assume that putting the detector there has changed the behavior of the particles in some way.
Well, that's an
Some
assumption.
people would say it's putting the detector there. Some people say it's the observation. There's, but something about the way that experiment changes has changed the result.
Right. And the common way that people, or is the initial instinct that a lot of people would have when seeing these results would be that the detector has somehow altered the course of the electron in some way, or that the detector itself is mechanically changing what happens. And that's John, maybe you can speak to this, but that's not considered to be a correct interpretation anymore, right?
Well, let's see. I mean, the thing to understand is that it's not merely that the detector seems to be interacting with particles in a way that prevents the interference pattern, but maybe if we had a better detector, we could just so gently observe the particles that they would still do what they were doing before and go through both slits. It's rather that there seems to be a fundamental limitation where if you try to observe this particle behavior, then you get the particle behavior. And you only get the wave behavior when you do not try to observe the particle behavior. So, for example, one of the things you can do if you're passing electrons through the slits and using a light source to observe which slit the electron went through, you can turn down the intensity of the light source and say, okay, maybe that will be a more gentle way to do this observation, and maybe I'll get the interference pattern back. And what happens when you turn down the intensity is, well, because light also has this particle nature, at some point the intensity is low enough that individual photons are being emitted from the light source. And so sometimes you get the same thing you got before, where you see a flash of light from the left slit, or you see a flash of light from the right slit, but sometimes there's just no photon there and you don't see anything at all. And now it turns out when you keep track of how the particles are building up, how the sort of points of detection are building up on your detector screen, what you see is that for the particles for which you did have an observation, there's no interference pattern, and for the ones for which you didn't, there is an interference pattern. So there's really something fundamental about that.
That just blows my mind. It's like, yeah, it's like the electrons are like trying to hide from you, or they're embarrassed, when when they see that they're being observed, suddenly they can't, they can't just act natural.
It's really weird because it does seem like either the presence of an observer or the fact that a measurement is taken, like somehow the fact that the particle is being watched changes its physical nature at a pretty fundamental level.
Something like that has to be going on, and in the earliest way of understanding these experiments, that's exactly what people said was, something different happens when a measurement is taken, and that's concept is associated with what people call the Copenhagen Interpretation, which says you follow these wave-like laws of quantum mechanics until a measurement is taken. And when a measurement is taken, then some kind of collapse happens where a decision is made about what's really going on. And so in this two-slit experiment, where you let the particles propagate to the screen before you try to interfere with them in any way, the measurement is taken at the screen. But when you try to observe which slit the particles go through, the measurement is taken at the slit. And it's when that measurement is taken that something else happens, and this wave-like behavior collapses and gets turned into particle-like behavior.
It's so strange though, because like, what is a measurement? Like, it seems to me like if no one is observing which slit it goes through, then it's still influencing matter at those slits. Like, it's still like photons are bouncing off when the electron goes through one slit, or something is happening at some physical level there. Like, there's some physical thing happening at that slit. But why isn't that considered to be taking a measurement? Like, it almost seems like it's only considered to be a measurement if there's like some intentionality behind it, which seems really strange.
I'm not sure that intentionality really plays into it. If the, if the particles are sufficiently disturbed in such a way that you can read out what happened afterwards, then you won't see the interference pattern. So you have to be careful about the experimental setup. If you if you have some sort of accidental light source which is interfering with the electrons, then indeed you won't see the interference pattern.
I don't know though if that's actually how it works. Like, do you know about the delayed choice quantum eraser experiment?
Indeed. You start with a two-slit setup, and you orchestrate things so that you can read this what you call the witch path information, which slit the particle went through. And the way you do that is through entanglement, where there's ways you can take a quantum particle, just any particle, in fact, because every particle is a quantum particle, and pass it through some kind of special crystal or some kind of special material where it can interact in such a way that it decays into two particles. To be concrete, these are photons in the experiment we're talking about. You have one photon decay into two, and basically just due to conservation properties, you know that there's some those two sort of output particles have to be related in some way. So using that information, you can set up a two-slit experiment and set up a detector screen, and you add this additional device which creates this entanglement. So you have one particle going to the detector screen, you have another particle going somewhere else. And by reading that other particle, you can do a measurement on that other particle and figure out what happened to the first particle. They are linked through this thing called entanglement. So that's how you do the measurement in that experiment. And when you do that experiment, when you do that measurement, you don't see the interference pattern. Now, the interesting thing that happens in the quantum eraser, and the reason why it's called a quantum eraser, is there's a way you can do a measurement on that entangled particle and actually recover the interference pattern. And in order to do that, you have to know that there are different ways you can do measurements on these particles. So a simple example of that is if we're talking about photons, you can have a polarization filter, and you can turn the polarization filter, and when depending on the angle of the polarization filter you are measuring, you are deciding whether light is polarized at this angle or whether it's polarized at another angle. So you have there's some choice you can make there.
So I want to get a little bit maybe less technical. Basically, my understanding at a very basic level of what's happening in the quantum eraser experiment is you take a measurement of which path, which slit the photon went through, the electron went through, let's say. And with the photon carrying that information, you basically delete the measurement after it's been taken. And by doing that, you delete your ability to find out which path, which slit the electron went through. And by doing that, you get the interference pattern back, even if the information was deleted after the electron hit the slit, or after the electron hit the, what do you call it? The photographic plate, the place where the interference pattern would appear.
Right. So the thing I'm trying to get to here is that you get the interference pattern back, but you don't get the interference pattern back in the sense that what's on the screen changes. What's on the screen is not the interference pattern, and it's still not the interference pattern. But when you measure that entangled particle in the right way, you get one of two outcomes. And if you look at the sort of dots that appeared on your detector, which correspond to one of those outcomes, you see that those dots form the interference pattern. They form an interference pattern.
But basically that happens when you delete the which path information, right? Because like if we say measuring it in a certain way, but the specific way that you're measuring it is you're measuring it in such a way that the which path information can't be recovered, right?
That's correct. You're measuring it in a way which is not the normal way of figuring out which slit went through, but a different way, a way which is in some sense rotated.
Yeah, well, it's a way that makes it impossible, right? Because it's like you have the Heisenberg uncertainty principle in quantum physics, right? Which says it's impossible to know a particle's momentum and position at the same time. Some people interpret it like a particle doesn't have a momentum and position at the same time. And so if you have data stored in the position, like if you're like, this position means this, then you measure the momentum, then that position data is lost forever. And that's basically what you're doing to the which path information in the delayed choice quantum eraser, right?
Correct. After you've made that measurement, you can no longer recover the which path information.
And you get the interference pattern.
You can recover the interference pattern.
That is what that experiment shows, right?
I'm interested. What do you mean that you can recover the interference pattern, but it doesn't?
So what's happening is you have this detector screen, and just like in the regular two-slit, particles are appearing one at a time on this detector screen, and some pattern is building up. And meanwhile, off to the side, you're measuring these entangled pairs, these corresponding particles.
Right.
And because you time things very precisely, you know the correspondence between the dots that are appearing on the detector screen and the measurements you're making of the corresponding particles.
So to be clear, so I understand with the quantum eraser experiment, you have basically a whole bunch of electrons hitting the screen. Some of them correspond to this measurement pattern where you're measuring the particles in such a way that it deletes the which path experiment. Some of them are corresponding to ones where you preserve the which path experiment. And my understanding is that if you separate out the patterns that the electrons in those different categories produce, then the ones where the which path information is preserved don't have an interference pattern, and the ones where maybe there's a level of complexity that I'm missing here.
I think what you're saying sounds totally correct to me.
Okay.
The thing I wanted to clarify is that it's not that some pattern appears on the screen and then you do some measurement which is supposed to erase some information and then the pattern changes. The pattern on the screen is fixed, but you can still recover more information because you know this correspondence.
Just to totally clarify, John, from what I understood from what you just told me, it was a lot of technical detail, but it seems to me that at a very basic level, what the quantum eraser experiment seems to be showing is that in a case where a measurement is taken, but then the measurement is destroyed before being recorded, even if that takes place after the electron hits the photographic plate or whatever, then the electron will show an interference pattern as though it had never been observed. Is that accurate?
I think,
and I guess by showing an interference pattern, I mean if you isolate it and from the other electron, I get that there's a methodological process to make that happen, and you're not literally seeing the interference pattern. You have to abstract away the electrons that were observed, and that's a mathematical process. I get that, but that's a methodological issue. At a conceptual issue, the electrons are behaving. If you were to set up the experiment, if you were to set up the experiment in the exact same way, but instead of deleting the measurement, you were just never taking it, you'd just get the same results, right?
Yes, I think that all sounds correct. Yes, so the interesting thing is that it seems like you can take this measurement and destroy the interference pattern, but it's not really lost forever by taking this additional measurement or by taking this sort of rotated measurement, which doesn't give you the which path information. You can recover that information, that interference pattern. You can recover that information.
Yeah, you're recovering the interference pattern. I mean, I think the way we're talking about it, I feel like there's a lot of double negatives, so it gets kind of confusing. Basically, maybe I'm just trying to put it in as simple terms as possible. because I think I understand what you're saying, but basically the idea is if the electron is never observed, it behaves like a wave. If it's observed and we take a look at the observation, it behaves like a particle. If it's observed, but we destroy the observation, which I know we can make it more complicated, but let's keep it at that for now. If we take it and we destroy the observation, it behaves like a wave again. Is that basically, like, I know that's we're simplifying away all kinds of in details, methodological details, but that is accurate, right?
Yes, there's a sense in which that's true.
I think that if we take away all those details, though, then we're making really general statements. And I'm wondering if, like, a lot of us take the quantum eraser experiment to mean that, like, it's definitely the observation itself and, like, the knowledge that collapses the wave function. But I'm wondering if you zoom in on the details, perhaps, John, is it your position that the quantum eraser experiment still leaves room for something physical happening with taking the measurement, or what it means, like, actually literally to delete the measurement, that it's not about whether the knowledge is actually retained, but it's something in the experiment itself that's, like, physically interacting with the particles and changes how they behave?
Let's see, I have to sort of parse what I think you mean by that. Is it...
Like, does the quantum eraser experiment definitively prove that it's not something physical about the act of measurement, and how when you fire the photons to measure what's going on, it hits things and changes the behavior? Does the quantum eraser experiment prove that it's not something physical like that going on, but it is in fact whether the actual knowledge is retained and measurable, like, conceptually?
Well, it's all something physical going on. So I'm not sure how to say that any other way.
I mean, I think the question is, does consciousness cause wave function collapse?
No, that's not the question, Chris. That's way more general than the question Katie's asking, I feel. I mean, if maybe the question is more like, does the photon itself mechanically, like, is the mechanical act of measurement what causes the wave function collapse? Or does the quantum eraser prove that the mechanical act of measurement itself is not what causes the wave function collapse?
So I don't think so that is going to become an interpretational question. Not necessarily exactly what Chris is saying, but it's going to become an interpretational question. The results of the quantum eraser experiment are exactly those predicted by the physics of quantum mechanics. There's not new physics in that sense.
Yeah, but quantum mechanics is pretty, like, it's like this view that Katie is kind of asking, like quantum mechanics already repudiates this idea that particles have a pre-existing set of classical coordinates that are always present whether we observe them or not.
Right. Philosophically, I think that would be called realism. I hope I'm not misusing that term. But
yeah, exactly. Like, quantum physics already, like, quantum mathematics has already poses a lot of problems for realism. So it's not like the quantum eraser experiment is introducing this new anti-realism or subjectivism into quantum physics that didn't already exist for, like, 80 years or whatever, right?
That's correct. And, that definitely becomes an interpretational question now. I mean, there are realist interpretations of quantum mechanics, and there are non-realist interpretations of quantum mechanics. The difference between those two is basically locality, which means, we'll get into what people call local realism, which I think is sort of, in my view, as not really a philosopher, is sort of the central philosophical problem with quantum mechanics. Which is that you can come up with a realist story about these particles really do have, there really are concrete, definitive numbers that describe their state all the time. But then they have to, in order to make that happen and agree with the laws of quantum mechanics, they have to interact in some non-local way. Or in the case of the quantum eraser, perhaps in some retrocausal way.
These local, but by these local numbers, you mean stuff like position, momentum, mass, energy, like stuff like that, right?
Yes, correct. All the numbers that would describe the state of a particle.
Right. So when we're dealing in the classical world and we're watching like a ball roll down a hill or something, we're able to ascribe those numbers to the ball and be like, the ball has position, momentum, force, energy, it's doing this amount of work. And it's easy for us to say in the classical world, it seems to be that that ball would have all those numbers whether we observe them or not. It's just doing its thing, and we can observe and we can not interfere too much. We can figure out the numbers, and if we kick the ball off its course accidentally by measuring it, then that's our bad because we're measuring too harshly. And that's how the classical world works. And I think a lot of us would like to believe that the quantum world works that way, that when we're taking a measurement, we're just kicking the electron off its course and that it always had these numbers. But we just have trouble figuring them out because they're so small and tricky. But it seems to be that quantum mechanics is telling a different story, that these things work in a very non-classical way.
Yes, precisely.
Maybe this would be a good time to get into Bell's theorem, which I think maybe you, John, or Ariel could explain a little bit better. But I think that Bell's theorem and that experiment does a better job of kind of showing how we know that if there is information about the particles at any given time, it at least isn't local, right? It at least isn't contained within the particle itself.
What's the best way to go about that? So it's in the classical world, it's often the case that you have two different particles that are, there's some relationship between them. Often, if we're talking about some kind of physics experiment, it's also often because of some conservation law. Two particles were spontaneously emitted from some other particle that decayed, and so by conservation of momentum that they have to have opposite momenta sort of in the frame of the original particle. There's nothing mysterious about that. Without talking about physics experiments at all, you can set up correlations in the classical world by saying, I flip a coin and then I write heads on one card and I write tails on the other card, and I mail one card to Alice and I mail the other card to Bob. And now, when Bob opens his envelope, if it says tails, Bob instantly knows that Alice has an envelope that says heads in it. And there's nothing mysterious about that. The interesting thing about quantum mechanics is that, the interesting thing about quantum mechanics is that when you create two particles which have some kind of linked property in this way, because of this sort of dual nature, or this sort of incompatibility of different measurements having definitive values at the same time, you get these effects like the one you see in this game I've described, where you can create correlations that couldn't exist classically.
Basically, in a nutshell, I think you did a really good job describing the math, and I think it's challenging to do so without using visuals. In a nutshell, from my understanding, Bell's theorem shows that when you have these two entangled particles, and there's a situation where if one is heads, the other must be tails. People consistently observe that if they look at this one and it's heads, then that one would be tails. But you could just say, okay, well, they're like Bob and Alice. They just had heads and tails labeled to them when they started moving apart. So of course, it's going to be that way. But basically, Bell's theorem shows that probabilistically, the math doesn't work out that way. And in fact, when you look at this particle and it says tails, then that one didn't say heads before that moment. or at least heads wasn't locally stored within that variable itself until before that moment. Is that accurate?
When you have received some particle, which is part of an entangled pair in this case, there's a choice of measurements that you can make. We spoke about position and momentum before. It's a little hard physically to conceive of how this would be set up, but you can imagine that you have a choice of either measuring the position of the particle or the momentum of the particle. And the interesting thing is that those, as was alluded to earlier, those two measurements are sort of fundamentally incompatible in some way. If we assumed that there was some definitive value for the position and for the momentum, then everything would, again, just be like in the classical scenario. And it would just be like as if there were two different cards, one with the position written on it and one with the momentum written on it. And then, there would be no way to win this game that we've described, or in other words, to violate the Bell inequalities. But it turns out that there is.
So it basically, in a nutshell, what this suggests is that particles don't have these properties like position, momentum, I don't know, energy. They don't have. There's a set of properties that they can't have all at once.
Either that, or you have to concede that, yes, either they do not have definitive values for all these properties at once, or you have to concede that somehow some communication would have to be going on, and it would have to be non-local communication, because if you believe that all these values existed with definitive values beforehand, in order to make these correlations happen, when Alice does her measurement, somehow the value of what Bob's measurement is going to be has to change. And we set this up so that Bob is far away, and Alice and Bob can do their measurements simultaneously to whatever degree of precision you desire. So either we have to believe that these definitive values didn't really exist beforehand, or we have to believe that there's some kind of non-local behavior going on where the definitive values did exist, but they're changing, and they're changing, they're changing non-locally. They're changing even though these two related particles are separated by some large distance.
Okay, so non-local basically means like maybe Bob and Alice did each have like a piece of paper that said heads or tails, but as soon as one looks at it, the other one's paper changes.
In some sense, yes. That's what a non-local interpretation of quantum mechanics would say.
That's what a non-local hidden variables interpretation would say, right?
Right.
Okay.
And then another interpretation would be that they never had papers that said heads or tails definitively. The papers kind of said both, and the words were like wobbly and wavy. And then when you measured one, then both of them snap into place. Those are the two options, right?
Yes. Sure. Yes. So yes, it is the case that yes, succinctly, entanglement is when you have two quantum particles whose states are linked in some way.
Where basically you can have, they can both be in superpositions of states. Okay, so this is what I was just thinking of. So you have, two particles that are entangled, and you send them to opposite sides of the universe or whatever. And, Alice receives one and Bob receives the other. And they're both basically in this superposition of states until observed. And I guess the interesting question is, like, when Alice observes her particle, does that immediately collapse Bob's particle, or does he have to actually observe his particle in order to collapse his particle? I guess that kind of derails the conversation a little bit. Sorry.
No, I mean, that sort of gets into this interpretational question of, if you want to preserve locality, then you must sort of believe that there is no definitive state of what Bob would measure when Bob makes his measurement. And if you want to preserve realism, then you must sort of believe that there's some non-local interaction between the measurement that Alice made and what Bob will observe when he makes his measurement.
And importantly, to preserve realism, it would have to mean that this interaction is happening faster than the speed of light.
Right, that's an important...
Which would mean that maybe you could have causality that could go backwards in time.
Well, so
it's still not super realist.
Well, so if information travels faster than the speed of light, that's extremely problematic because, as you said, causality could go the other way. In fact, there would be some reference frame in which causality would go the other way.
Right.
So that's extremely problematic.
Yeah.
Now, it turns out that...
So it's problematic whichever way you want to go for like...
Well, but it turns out that the laws of quantum mechanics that we use to win this game in this case, they're at this subtle boundary between these two possibilities where if you believe in non-locality, there's some kind of non-local interaction going on, but it doesn't let you communicate. It doesn't let you send information. So there's no problem with causality in that sense.
There's no problem with causality except that the states aren't defined, right? So you have like this element of randomness where things are undefined at this very tiny level. So you don't really have deterministic causality. Like either way you shake it, we don't have normal causality the way that we like to think of it day to day, right?
Well, I mean, again, sort of all I can say is that you don't have local realism. Either you say that you do have deterministic hidden variables is the term that was brought up. You do have these deterministic hidden variables that really determine what you will measure for any measurement you can take. But
cause and effect can go backwards in time.
Well, it's not that cause and effect can be backwards in time, but there has to be some kind of non-local interaction. Now, there are other interpretations of quantum mechanics, which I'm not very familiar with, which are retrocausal interpretations, which I think attempt to preserve a bit more locality and also realism, but add this aspect of retrocausality. Unfortunately, I can't go into too much detail about that because I don't know too much about that.
Okay, so maybe it would be helpful to break it down. I'm trying to understand this too. So there's like a few factors that we want in order to be able to preserve our pretty view of the universe that makes sense. We want causality. We want there to be cause and effect. We want particles to have properties at any given time, like that are real and tangible and determined like within the particle. So we want local realism and we want causality. Otherwise things are kind of weird, right? And basically all these experiments show that we can't have those things at the same time. It's not consistent with everything we've observed, right?
Yeah.
So the world is weird, definitely.
That's certainly the standard philosophical conclusion of what we've learned from the Bell inequalities, and these things have been experimentally tested.
It's definitely weird in some way. It's definitely not. There's no just like cool explanation for this that isn't gonna fuck with us somehow.
Yep, I think that's inarguable at this point, and that's certainly been hard for some people to swallow historically. for a long time at the beginning of quantum mechanics, there was a feeling with a lot of people that we would figure out that this is all just a statistical theory, and there's some underlying theory which again would be a locally real theory, sort of in the sense of thermodynamics, where you imagine there's all these little particles doing real definitive things, and the observations you can make are only statistical, but something real is going on. It's just probability. But what we've established pretty definitively now is it's not just probability. And it's not just probability because these things that look like probabilities, they can interfere.
Yeah, my first instinct when hearing about, oh, well, at the quantum level, reality is just probabilistic. My first reaction was, well, you use statistics in a situation where you don't have all the information. So clearly we're just missing some information. Right. But yeah, I guess quantum is saying pretty definitively something different is going on.
Yeah, we could have it be just probabilistic. We could have these non-local hidden variables that are communicating faster than the speed of light. We could have, well, there's a lot of different things that we could have, right? Like there's a lot of different interpretations of what all this means. And every possibility is wonky.
Yeah. Yeah, it seems like the many worlds interpretation is one where a lot of intuitive concepts can be maintained at the cost of believing that the world is constantly bifurcating into multiple parallel universes.
Right. So one way to sort of deal with what's going on with all these things we've talked about is to say, well, this sort of odd behavior arises when you take a measurement, and we haven't really said definitively what a measurement is. And really, the laws of physics, there shouldn't be different laws of physics between when you're not looking at things and when you're looking at things. Everything should just follow one set of laws, and maybe that should just be the laws of quantum mechanics that we've established. And so you can write that down and see what would happen. And when you write that down, you of course have to include yourself in those equations because you are part of the quantum system now. And then the interesting thing that happens is that when you follow the normal laws of quantum mechanics, the term that corresponds to you, the observer, when you observe a system in superposition, that term will appear twice. In other words, you will enter that superposition. Mm-hmm. And this all works fine, and it's a local theory, and in some sense it's a deterministic and realist theory. The thing that happens that makes many people uncomfortable is that you appear multiple times in the description of the universe in sort of irreconcilable ways. You can no longer be factored out of the equations. There are multiple U's, which, one corresponding to each of the possibilities that you could have observed. So you can, if you believe in the many worlds interpretation, then we just stop there and we say, well, there are multiple U's. That's how it works. If you find that very uncomfortable, then you must find some way to get rid of all the other U's that aren't the one that's actually you.
Yeah, so basically, just to summarize, one of the explanations for this weird phenomenon that seems one of the most reasonable explanations is that when you as an individual observe what's going on, when there's multiple possibilities, the universe splits into however many possibilities there are, and there's multiple U's existing in these multiple universes, and like every time that a superstate is collapsed, there's a new universe with a new you, and you're having an impact on that.
Yeah,
that seems rational.
Terminology is kind of regrettably sensational, and when we say that it's called the many worlds interpretation, and that wasn't originally what it was called, but that term became popular at some point.
And is it just the terminology that's sensational there?
It is the terminology, and maybe it's also the physics, but the way in which the terminology is sensational is you talk about these many worlds and you talk about things splitting, but it's not really, there's no special process of the universe splitting. In fact, it's the least special process. What's going on is the least special thing that could possibly be going on, which is just the regular laws of quantum mechanics are happening. And in the regular laws of quantum mechanics, you have superpositions. Even if you believe in the Copenhagen interpretation, you have superpositions of microscopic particles. The sort of additional thing, which isn't really an additional thing, but the additional thing that comes in with many worlds interpretation is that you say, I just keep going, and now there are superpositions that involve macroscopic things. And as things continue to interact, the superpositions involve the whole universe.
I mean, in terms of the math, maybe that's the least special thing that could be going on. But unless I'm misunderstanding it, that seems like a pretty special thing.
So the special thing is that the observer, and there's nothing special about the word observer here, any part of the system we're describing which starts interacting with other parts will end up appearing in multiple places in that description. And that includes when that part of the system is the observer, a person, a dog, whatever.
It seems to me that one of the implications of the many worlds interpretation is that going through life, you're constantly observing things at all times. And so are we just constantly bifurcating reality every time we look at anything, or maybe understand anything? Maybe there's some kind of higher level thing going on. I don't know.
I heard one interpretation that basically before the age of modern physics, before the 20th century, it's possible to believe that reality was just deterministic, that we only operate on the classical level, and on the classical level it's possible for everything to be deterministic. If it's the case that classical phenomenon, the objects at this size don't collapse any kind of wave function, then it's possible that up until the 20th century, everything was just deterministic and everything only happened once as far as human beings were concerned. And then when we got into the 20th century and we started looking at particles, then every time we looked at particles, the classical world bifurcated. I actually know someone who's a physicist who was, had some kind of PhD in physics, who was who literally went and looked at a particle detector experiment and looked at the outcomes. So they were okay, now there's at least two of me.
It reminds me of the theories about the LHC, about how it created a supermassive black hole and ripped a hole in reality or something like that. It's no, these physicists, why are they screwing with reality? They're gonna mess it up in ways that we can't predict.
I mean, it's probably not true, because they found that metal paddle, I mentioned, the metal paddle that's showing that can be in a superposition. So it does seem like the evidence is pointing towards the idea that macro objects can be in superposition, which I understand is unsettled, but it's interesting. Who really knows what studying this stuff, what effect it has on reality?
I mean, you have to. The thing to understand there is that you have to work hard to keep things in superposition, which is sort of part of the reason why it's so hard to build quantum computers, for example. But this sort of process of observation or of things falling out of superposition, it's very easy to do that accidentally, because particles normally interact with all the things around them.
Okay, that's one interpretation. Another interpretation, and I'm not a physicist, but the way that I would think about this, if I were going to go down a many worlds train of thought, is there's lots of teeny tiny things happening within our own minds all the time, and our mind, our consciousness is observing itself all the time, right? So would it be a reasonable interpretation that within our own minds we're constantly bifurcating things by observing what's going on within ourselves?
Well, yeah, I mean, this this sort of bifurcation only happens when one system is interacting with another system which is in superposition. So, you know, the brain is kind of a very kind of like warm object where, you know, things are not well isolated, and it's sort of hard to believe that kind of the sort of somewhat more macroscopic structures that are actually involved in thought, if we're, you know, talking about you know, neurons and axons and dendrites and, you know, things you can see under a microscope. You know, the actions, the things that are going on there to, you know, carry, presumably to carry thought, those are not things that are happening in quantum superposition. Those are things that, you know, you can look at, you can stick electrodes in someone's head and read out what's going on.
But I don't know. I mean, they found quantum effects with buckyballs. Buckyballs are far larger than neurotransmitters. And from what I can, the little I've studied of this, they've found quantum effects taking place in, like Chris mentioned yesterday, like living tissue, proteins, the way that proteins fold, there's a quantum element.
Yeah, apparently photosynthesis involves some kind of quantum transfer of energy.
Well, sure. It all depends on what exactly you mean and what is meant by quantum in that case. I mean, of course, we're talking about sort of biochemistry now. So at the level of chemistry, chemistry is explained by quantum mechanics. So all chemical effects are quantum mechanical effects, and, you know, all molecules individually obey the rules of quantum mechanics. Now, if we're talking about the operation of the brain in particular, you know, it's not, you know, I don't think it's generally believed that, you know, individual neurotransmitter molecules are, you know, orchestrating thoughts sort of on that microscopic scale at the level of chemistry and at the level of quantum chemistry. You know, it's normally believed that that's done by neurons, and you know, they fire these action potentials, which you can read out in a very coarse sense.
Okay, now this is the thing that I know about to some extent. The brain is an electrochemical machine. That's one way of thinking about it, at least. So the brain is an electrochemical system. So you have like the action potential traveling through a neuron, but at the end of the neuron, it releases a neurotransmitter that then diffuses through the synapse to the next neuron. So the way the signal works is it's like electrical, chemical, electrical, chemical, electrical, chemical. And it's often interpreted in a Newtonian way. Like that's the paradigm that we're on. It's like if you're depressed, we'll just put some more dopamine in and then you'll be less depressed. And that system works to a certain extent, but it works very imperfectly. And our knowledge of the brain is very, very limited, very imperfect, particularly when it comes to some of these issues that Katie brought up, like choice, consciousness, stuff like that, free will. We do not have a scientific explanation for these phenomenon. And I guess what I'm trying to point out is we don't know. Like, we don't know to what extent, we don't know to what extent quantum phenomena like impinge on the functioning of the brain. We do seem to know that there's some element of quantum physics does impinge on like protein folding and photosynthesis. So it's not entirely like quantum biology is like an emerging field, but there definitely are structures in the brain that are small enough. Like that's undeniable.
Well, everything is I mean, there were a lot of things you got into there, but let me just say, I mean, everything is made of molecules. So, you know, everything has a length scale on which you know, quantum effects happen, and you know, you can't understand what's going on without following the laws of quantum mechanics. That said, to my knowledge, there's no indication whatsoever that those quantum effects are important in the actual operation of the brain.
So just back up a little. There's actually, if you Google quantum photosynthesis, experiments confirm superpositions occur in light harvesting bacteria. And that basically just, you were saying, I kind of highly doubt that there are these quantum superpositions happening in the brain because it's this, you know, warm, you know, chaotic environment. But yeah, apparently there's
So I mean, we're jumping between totally different.
Yes. When it comes to the brain, though, like you say, there's no indication, but I mean, our knowledge of consciousness is like 15th century. Like in the 15th century, I could have said there's no indication that, pick any modern scientific, there's no indication that tiny invisible creatures make us sick. Like you could have said there's no indication. When your knowledge of something is very primitive, you can say that there's no clear no clear path to the solution, but there's no indication also that quantum phenomenon are completely irrelevant when studying the function of the brain. And there are like specific instances where we can think of where very small molecules are acting in some degree of isolation, like when they're diffusing through the synapse.
Well, I mean, I probably have to say here, I'm not a neuroscientist. I'm not a lot of things, it turns out. But I don't think it's the case that we know so little about the brain that we could say, you know, it could very well be that thoughts exist in quantum superpositions. You know, we've intensively studied nervous systems, and we know quite a number of things. My specialty in computer science is in computer vision, so I know a little bit about what people know about the visual system, and you know, we know very definitive things about you know, how light impacts the retina and how that gets translated into these electrochemical signals, which pass along neurons. And you know, you can stick electrons in, it's usually cats, but you can stick electrons in any nervous system and measure these signals, and you can make sense of them. I mean, you can see, okay, light hitting the retina has this pattern, that's what lights up this neuron. And sure, you can go to other parts of the brain and say, well, I don't really know what this neuron does, I don't understand it, and there's no global theory of like, how do we actually come up with thoughts, and how does our global perception of ourselves sort of arise out of that. There's a lot unexplained. But on the sort of microbiology level of how do individual neurons work, you know, I'm, at least personally, I'm pretty convinced that the output of a neuron doesn't depend on some kind of quantum superposition.
Well, no, but you're talking about, you're focusing a lot on the level of the neuron, which makes sense because if you're looking at computer vision, there's a lot of very long neurons transferring electrical signals long distances there. So, which is a more Newtonian process. Like I'm not really contesting the idea that what happens within a neuron is pretty Newtonian. What I'm saying is, for me, from what my limited knowledge of this, it does seem like what happens between neurons is happening at a scale below what we've observed quantum phenomenon at. So it doesn't seem completely crazy to me that stuff there, that there could be some quantum effects happening there.
I'm including in this, you know, what is happening between neurons. You know, it's certainly the case that we can, you know, grow a small collection of neurons, you know, in a petri dish or wherever you grow neurons, and see that, you know, when the outputs of these neurons fire in a certain way, you know, you can see the output of the neuron that's connected up fires in a way that you can model. And you know, it's not those models have a certain level of precision, and it's not you know, this field of study is not complete, but how neurons communicate, I think, is pretty well understood, at least on the basic level of sort of how thinking gets done. And I mean, if
no, but they don't know how it maps onto thinking at all. Like they know some things, like how the light signal passes from the retina to the occipital lobe, but again, that's a process where you mostly have nerves just bringing the signal back. There's no synapses in that process, and then once it gets there, oh, now it's a total mystery for the whole rest of the brain. Like you can't make the assumption that just because we know retina fiber that explanation will be isomorphic to how it works everywhere else, where it's completely shrouded in mystery and we have no idea how thoughts and the subjective experience map onto the physical.
Well, thinking may have been too strong or too vague of a word. But you know, it's not the case that it's simply the neurons in the retina and we look at the outputs of those and we see, oh, those correspond to the inputs. I mean, people go beyond that into the visual cortex and say, okay, there's a layer called V1. There's something called LGN in between that, and these things are connected up in layers, and you can go and see higher layers of structure. You can see, okay, this thing responds to certain patterns where things in the visual field have a certain angle, and this one responds to blue dots in a certain location, and then and you can see that they're all arranged in a certain way that kind of makes sense sort of anatomically to sort of represent the whole visual field. So I mean, there has been a lot of study in this field, and there's a lot that's still to be explained, but there's a lot that has been explained, and there's nowhere in those explanations does quantum superposition enter into this.
No, but I mean, those explanations are incomplete, and we don't know what's going to be required to complete them. And I mean, those kinds of explanations that you're talking about, like regional explanations and like single neuron explanations, like they work pretty well for something like the visual cortex, even though those explanations still run into problems there. But like, you don't actually have a neuron for blue. Like you don't actually have, like, you have a very limited number of neurons. Like it's not like there's one neuron for each thought you have, or one section of the brain for each thing you do. It's much more complicated than that. And like the cutting edge view of how the brain works now is that it's network effects. Like that's the current paradigm. Not like they started with single neurons, and they were like, oh, what we can explain with single neurons is actually extremely limited. Well, maybe it's brain sections. And then they sectioned off the whole thing, and they were like, this gives us some information, but it's very imperfect. It's very imperfect and doesn't seem to map well onto how thought works at all. It's like, it's like taking a 15th century. It's like, that's why I say it's 15th century. It's like you take a 15th century map of the world, and it's like, Europe is this giant thing, and there's dragons on this side, and I don't know, they kind of know that India exists, and they're like, see, look how well we've mapped the world. There's not much more to know. But that's exactly what we have of the brain. It's like a 15th century map. And
sure, I mean, your point is well taken. It's certainly true that we do not have a global theory of what the brain is doing, and there's a lot unexplained about the brain. But we're sort of, when you say, well, we understand individual neurons, but we don't understand really what collections of neurons do together, it's true. But it seems like we're going in the wrong direction to bring quantum mechanics into this.
I'm not saying we should necessarily bring quantum mechanics into this. Like, I'm not writing a research paper. I'm just saying I think discounting it is also, especially when the issue that caught us into this is when Katie brought up the idea of like choice and consciousness and free will, which are issues that are still very much in the realm of philosophy, which tends to occur when science in a particular area is at a primitive position, as it is in this case.
Yeah, I think what I'm trying to say is that it's not merely that there's something unexplained and it might be quantum mechanics. It's that there's something unexplained and there's sort of no way to imagine that it could possibly be quantum mechanics.
We don't have any way of understanding how the brain itself as a physical object gives rise to a subjective experience. We don't have any mechanism for that. Everything that we understand about the brain could work. Everything that we understand is so Newtonian that you could do it. You could just program a machine to do it that doesn't have subjectivity, and it could do it. Like, I'm not saying that everything, I'm not making the claim that everything the brain does could be done by a machine, but everything that we currently thoroughly understand about what the brain does can be mapped by a machine that doesn't have subjectivity. So clearly we haven't found that mechanism that produces subjectivity, and which is why I think it's fair to be more speculative about it, because we really don't understand anything. We're only looking at a 15th century map.
I mean, we're getting a whole other topic here. We have to say, what we mean by subjectivity, but I'll just say, my job is to program computers to do things that the brain does, and not, my job is not to emulate the brain. It's just to solve similar problems.
Exactly. That's what I'm saying. The things that we can get computers to do that the brain also does, like we're getting pretty good at computer vision, pick your poison, whatever, it's like computer vision. We have a certain understanding of the visual cortex, understand how it does certain things. And we can get the computer to do certain things. Like we can now get it to recognize objects pretty well and stuff like that, and to see outlines that things it couldn't do before. But all those things are possible to be done without subjectivity, is what I'm saying.
Well,
we can't make a robot that is conscious, because we don't understand consciousness at all. We're not even close to understanding it. We're so far away from understanding it that many neurologists still would rather not even discuss it.
Well, sure. I mean, this no longer seems to be about quantum mechanics per se, but if you want to say we can't make a robot that's conscious, but you also want to say we don't know what consciousness is, then it seems hard to defend that claim.
Well, I'm making the claim that I'm making the claim at the current time our knowledge of consciousness is so limited that we can't emulate it in any way, and we can't explain it. Anyway, go ahead, Chris.
Yeah, so I just wanted to point out maybe a couple of places where you guys might be talking past each other. John, you are talking about vision and, and how, computer vision maps onto the visual cortex and how that process is fairly deterministic and there isn't anything spooky that's happening. And RAL is talking about how, no, there isn't anything spooky happening in vision, but maybe there's something spooky happening in subjective experience. And maybe there's something going on in that process, which involves something, strange or quantum. I'm also wondering, Ariel, are you trying to suggest that maybe the brain is some kind of quantum computer?
I think I would have to know more about quantum computers to answer that question. I guess the point I was trying to make at a deeper level is I don't think it's a convincing argument to say everything we understand about the brain is Newtonian and non-spooky, therefore the whole brain is Newtonian and non-spooky, because it could just be that because the way that we're choosing to look at the brain, which is basically as a machine, is limiting our ability to understand the spookier parts of it.
It's also very difficult for us to understand spooky parts or know where to start with trying to study spooky parts. So, I mean, it makes sense that everything that we would understand would be the stuff that's easy to understand, right?
Yeah, I think I agree with the way the argument's been laid out there. I think the thing I would add to that is that the things we do understand about the brain are on a level which sort of I would say convincingly screams out quantum mechanical effects.
So, okay, let me flip the original question around and come at it from a different angle. Well, not really a question, but let me just go this direction. We're talking about the many worlds interpretation. We're talking about an interpretation which, it's just a possible interpretation where the observer bifurcates reality. So if we were to go with that interpretation, and you are the observer, would that philosophically make sense, or how would it make sense for you to have an observer that bifurcates reality, but there's nothing going on within the observer at the quantum level that's spooky?
Well, so it's not that the observer bifurcates reality. The observer doesn't have the responsibility here. It's merely that reality bifurcates because that is what the laws of quantum mechanics say. And
the reality bifurcates and the observer shows up in two places.
Reality bifurcates is again kind of a sensationalistic way to say it. What happens is, indeed, the observer shows up in two places.
So there's something special about the observer. Maybe it's not the observer's responsibility, but reality is bifurcating, and the difference between the two realities is that there's two different observers, right?
So the sense in which reality is bifurcating is precisely that the observer appears in two places.
Right. And we are kind of saying that the observer is like a person or a dog or something like that, right?
None of what we said so far about how the many worlds interpretation works depends on the observer being a person or like a conscious entity. The observer can just as well be a rock, but then it's hard to make predictions about what a rock would observe and then verify those predictions.
I don't see how that makes sense though, because it's like, if you have just something happening, like again, like reality itself happening doesn't collapse the ray function. Like there has to be a process of measurement and observation, it seems. And like, how does reality know when a measurement has taken place? Like if you just have something happening in isolation, like if you have a rock rolling down a hill, it's disturbing other rocks and stuff. It's just rolling down the hill. And my understanding is that that wouldn't be considered to be a situation where an observer was making a measurement. But if you have someone show up, like how does reality know what a measurement is if not by the presence of a conscious being?
If we're still talking about many worlds interpretation, then to clarify, reality does not know. There is no special process of measurement. There is no collapse of the wave function. Everything just continues on following the laws of quantum mechanics. It's only if we want to say that we're uncomfortable with ourselves or the observer of the experiment appearing in multiple places in the wave function, having observed different things in those different places. If we're uncomfortable with that, then we must say, well, actually, reality must collapse somehow to leave only one of those possibilities around. And then we have to say, well, what causes that collapse?
But it does seem like at a very basic level, the experiment shows that an observer causes the wave function to collapse. Sorry, Katie, you wanted to say something.
Well, okay. If we're working with a many worlds interpretation, then the observer shows up in multiple locations. If we're working with a Copenhagen interpretation, then the observer causes the wave function to collapse. But like in both ways, there's something special about the observer. And what's weird about this?
There's nothing special about the observer in the many worlds interpretation.
Okay. Well, except for the observer shows up in multiple places.
The only thing special is how uncomfortable you are with the observer appearing in multiple locations because you're the observer.
Well, I'm just saying, to me, that's special. For the interpretation to mean that like a person shows up in multiple places. Maybe we don't have to say that that's special, but
right. So to clarify, when I say there's nothing special, what I mean is there's nothing in the physical law that says something different happens here because this is the observer.
So I guess my question would be, going back to Ariel's image with the rock bouncing down the mountain, why does the rock bouncing down the mountain not appear in multiple places when it interacts with the mountain? But somehow a person measuring the spin of an electron, causes the person to appear in different places. So
if the rock were measuring the spin of the electron, then the rock would appear in multiple places.
But what does that mean? Like, what is it? What if it is? What if it is measuring the what if it is measuring the spin of electrons as it's bouncing down the mountain? Like what do we consider to be a measurement, I guess?
If it measures the spin of electrons as it's bouncing down the mountain, then indeed it would appear in multiple places in the wave function.
Okay. So here's another question, and maybe this is just something wonky with language, but physicists seem to always use the word observer and observation. And to me, just like linguistically, observer implies a perspective from which something is being observed, right?
Yeah, so I mean, the philosophically difficult part of this is that at the end of the day, in order to find out the results at the end of the day, the results of experiments must exist in someone's mind, right? This becomes a much more sort of basic philosophical problem even than getting into the specifics of quantum mechanics. But if an experiment happens and no one observes it, then in what sense can we say that it happened?
Good point.
But doesn't the quantum eraser tease out that difference though? Like you have a situation where, I mean, it just seems to, like the electron goes through one of the slits, or the electron travels towards the slits. It bounces off something. Like unless it's going through a complete vacuum the whole way, if it's affecting any kind of particle on the way there, then why isn't the photon in the observer? Why isn't why isn't the photon considered the observer? The photon isn't enough to be considered the observer. The photon has to be recorded in a way that can be where the information is preserved. Like that seems like that condition is at least necessary for it to be considered that an observation took place.
So just to clarify, if the particle in any of these two-slit experiments or any of these experiments interacts with some intermediary that in some sense wasn't supposed to be there, and is an intermediary which you could use to figure out which slit the particle went through, then the experiment is ruined.
But yeah, exactly. But that you can use. That's the key term there, that you could use.
Well, that's just okay.
You as a human being, I as a human being, like the photon itself can't be the observer, right?
No, when I say you can use, what I mean is just that the particle is disturbed sufficiently in order to know which slit it went through. So, you know, it could be that the electron, there's an electron passing through two slits and it interacts with a photon, but the photon is a very long wavelength photon. And so some flash of light happens, but the flash of light is just kind of like large and fuzzy. And it's so large and fuzzy that you can't tell where exactly the electron was at the scale of the two slits. Then you sort of like observed something, but you haven't disturbed the interference because your observation just like wasn't good enough.
But then I guess, and again, it's you observing something. Like it's like the photon and the electron bouncing off each other and nobody noticing. It doesn't seem to be enough to collapse the wave function. Like a photon alone, the photon alone in the forest that no one sees doesn't collapse the wave function of the electron.
Well, okay,
I guess we wouldn't know that, right?
Yeah, there are some subtle distinctions here. I mean, if you disturb the electron with a photon, which, you know, creates a flash of light that distinguishes, you know, that would be sufficient to distinguish which slit the electron went through, then the interference pattern will not be created. It doesn't matter if you like.
But now you're just using the
decline
passive.
to actually look at what was recorded.
But the object of that sentence is still like it would still have to be distinguished by a human. Like
no, distinguished by the photon that the electron is interacting with. So like you could run a two-slit experiment and do this measurement and have this measurement recorded in some ledger somewhere, and then you could say, I'm not going to look at the ledger. I'm never going to look at the ledger. Well, the interference pattern is still not going to be there even if you throw the ledger into a fire.
What do you mean by it still won't be there? Because if there's nobody to observe it, then...
No, you look at the screen and you see whether there was an interference pattern or not. You do not look at the ledger which records which slit the particle went through. You throw that into a fire. And what happens in that case is that the interference pattern is indeed not there. The observation had been made even though you threw it into a fire.
And so the difference between that and the quantum eraser experiment is in the quantum eraser experiment, the information is not just epistemically absent, it's metaphysically absent. So it's not just that it can't be read by us, it's that it no longer exists, right?
I wouldn't say metaphysically, I would say physically, but yes, there's a sense
physically, okay.
The information as to, yes, fundamentally that information as to which slit the particle went through is lost and can never be recovered.
Is the information the crucial point here?
It's
not what happened, but whether the information about what happened is recoverable?
In some sense, yes. In some sense, the information is the crucial point. I mean, and that's sort of in fact, there's a whole field called quantum information, which sort of precisely studies the way in which information can be, communicated and recorded and used as a resource in quantum mechanics. So there is this fundamental thing going on where the interference pattern is fundamentally associated with the loss of a particular type of information, the information as to which slit it went through.
What is your interpretation of why that happens?
What is my interpretation? Well, you can follow the laws of quantum mechanics and see what they predict, and they work perfectly well. And I'm perfectly happy with that. I think,
So you're not bothered.
Well, I am bothered. I don't want to say I'm not bothered. It's certainly very appealing to say, well, we've established the laws of quantum mechanics really quite well, and this uncomfortable thing happens where observers, macroscopic observers, ourselves, for example, appear in the wave function many times. And, that's uncomfortable. I don't have, personally, I don't have any sort of basic physical objection to that. I think from sort of a computer science or a computer scientist perspective, perhaps, what makes me more uncomfortable about this is that if you observe, let's say you observe n different two-state quantum systems, the wave function kind of blows up in an exponential sense. Because there are two possibilities from that first system you observe, and then two possibilities from the next system. There's now 4 possibilities, counting both of them, and then there's 8 and so on. So there's this exponential blow up. And, from the computer science perspective, exponential blow up is not a nice thing. And so it makes me uncomfortable because if I were now to say, okay, I'm going to sit down at my machine and code up the universe, I would quickly find, well, I can't do this because I'm just going to run out of memory.
But what about from not from a computer science perspective or a physics perspective, but from a personal perspective? How do you feel about this?
Well, I'm a computer scientist, so.
So you're upset that you can't program the whole world?
Yeah, the way you say it makes it sound, I don't know what adjective I want here. I'm upset, but I'm not merely upset. Like, this seems like fundamentally uncomfortable in the sense that, like, maybe I could very well believe that maybe there's something we fundamentally don't understand about quantum mechanics that is going to limit this kind of exponential blow up.
So, I understand that from a computer science perspective, this is kind of uncomfortable because you're imagining a future where you're trying to work with this and there's this exponential blow up. And so you can't code the things that you want to be able to code. But from an existential perspective, this is also uncomfortable.
Oh, sure. I mean, to be clear, when I say from a computer science perspective, I'm not thinking of myself like writing programs on a quantum computer in the future. That I'm perfectly okay with. What I'm thinking of is if I were to invent the universe from scratch, how would I do it? And somehow I would have to set up the laws of reality and orchestrate them in a certain way, and I would have to have information flowing around in a certain way. And I mean, if you really want to simulate the universe, there are certainly you're certainly going to have some issues. One of which is going to be simulating chaotic behavior, another which is going to be simulating quantum mechanical behavior. And it turns out that if you want to deal with this sort of exponential blow-up issue in order to simulate quantum mechanical behavior, there's a nice way to do that, which is by building a quantum computer.
Right.
So that sort of neatly solves that simulation problem in a sense, but it doesn't address the whatever fundamental philosophical discomfort one might have with needing to imagine that there's this sort of exponential amount of information written down somewhere to keep track of what's going on. Even though you can't read out all that exponential information, you sort of have to imagine that it's written down somewhere to keep track of what's going on.
Yeah, I mean, I guess a lot of the discomfort comes from, what's that?
I just said that's at least a little uncomfortable.
Okay, yeah, I was going to say, so I think a lot of the discomfort just comes from kind of recognizing that the universe isn't deterministic, that it is probabilistic, and that there is just uncertainty everywhere. And even if you and I guess this is a totally different question, but if there's no way that you could simulate the whole universe, right? Even if you were God and you had unlimited capabilities, you couldn't actually simulate starting from the Big Bang or something like that. You couldn't predict where it would end up.
If we want to talk about simulation, then indeed there are all kinds of other issues we will get into. I mean, not just the issue of determinism, but if you want to simulate the universe, you would have to do so with a computer, which would be inside the universe, and then that computer would have to simulate itself, and then there's a fundamental question of whether you're going to run into some kind of fundamental difficulty there that's going to prevent you from actually precisely predicting the future or not. But none of that, quantum mechanics doesn't have any bearing on that. that question can be asked classically.
Do you think quantum mechanics makes it seem like the universe is a simulation?
I don't think I have any. I don't think it has any. For me, it has any bearing on the question. It's perfectly possible to imagine, a simulation of classical reality. It's perfectly possible to imagine a simulation of a quantum reality, whether on a quantum computer or on a classical computer.
Well, the quantum reality is digital, right? Not analog.
Well,
which seems to resemble a computer more than the classical reality.
I mean, the question of digital versus analog is somewhat of an orthogonal question, is somewhat of a different question. It's true that when you make there's this sort of particle-like behavior in quantum mechanics or this sort of discrete kind of behavior in quantum mechanics where you observe a particle that can have one of a few discrete states and you get an output which is sort of definitively one of those few states. But in order to work out the physics of quantum mechanics, there still has to be underneath some numbers ascribed to the sort of what are called the amplitudes of each of those states, which are the things that are like probabilities but can interfere. And those amplitudes are those are continuous numbers. So in that respect, I don't think there's any difference just from the basic laws of quantum mechanics. I don't think those have any bearing on the question of, is the universe fundamentally discrete or continuous?
Okay.
So what do you think is the relationship between math and reality?
I think that's a little bit too kind of vaguely philosophical for me to say something meaningful, but
I don't believe you.
I mean, I think, there are people who think there's no difference and people who think math is a tool for describing reality. There's sort of this philosophical position that anything which mathematically could exist, like actually exists. And I don't know. I don't think I really have anything to say about that.
I mean, to me, the two perspectives are, math is a language that humans invented to understand the world, but it really, it may or may not actually exist in reality. And of course, the other perspective is that math is the language of the universe, and accurately describes the universe, and it's out there, and we just have to discover it.
Yes.
So, yeah. I mean, those two perspectives are interesting in different ways. We might be like a little bit off topic from quantum physics and what it implies. So, I think it'd be interesting to get into. I know that quantum physics implies some weirdness and maybe some weird. I don't know. The many worlds interpretation would imply some weird exponential universe growth, which would be difficult to deal with. But for us individually, and maybe I'm just taking this to a really basic level where others don't want to go, but this seems to have some weird implications for the nature of the self and reality and ourselves, emotionally. How do we handle showing up in the wave function multiple times? What does that mean for who you are and what your decisions are and stuff like that? I know we can't answer those questions definitively, but I think that that's something interesting to explore, and any conversation about this definitely should be.
Yep.
I mean, that's pretty meaty to everybody, right?
Mm-hmm. Yeah, definitely. I think it's an interesting thing to talk about.
Yep. So, to quote someone who I cannot recall, it all adds up to normality. The fact that you appear in the wave function multiple times, well, there may be interesting things to think about that, but it doesn't change your experience of reality. There's no possibility of being simultaneously multiple of those terms that appear in the wave function. You're always just one. So.
I don't know, John. I think the implications do matter. I think the things that we believe about reality influence how we act in the world, the lives we lead, and how we relate to the reality around us. Like, I mean, one thing I've heard a lot is like a lot of people seem to associate quantum physics with postmodernism, which is this idea that like is this philosophy where everything is kind of it denies realism in a sense too, or like it kind of is skeptical of objective realism, and it's this idea that the person, like the experiencer and the historical context they come from, is inextricable from whatever thing they're observing. Or so it talks a lot about like it focuses a lot on language and how language shapes our thoughts and how language shapes our experience of reality, and how our society and our history and our social upbringing influence our experience of reality. And so I've heard a lot of people like linking it with quantum physics.
Yeah, well, I took a short course in postmodernism in college for some inexplicable reason, but I think it's the postmodernists that associate postmodernism with quantum mechanics. It's not the quantum physicists.
Why do you think that
Yep.
physicists seem so chill about this?
I mean, maybe physicists are just chill people, but I don't know. Let's see. What do you really mean by that?
What I mean by that is, you guys are like studying these phenomena, which imply that reality isn't really real in the way that we think it is, and maybe we can think of it like the observation has, everything is happening at once, and when you look at it, then it's decided what happens, but everything is just probabilistic and there's not actually cause and effect. Or maybe reality is constantly branching into infinitely many realities, but however we look at it, something is really strange. And maybe it's just the way that physicists look at the world, but
Sure.
and not all physicists are like this, but that's
well, I think part of it
kind of emotionally like a tough thing, right? Like, wow, reality isn't real.
I mean,
Sort of.
certainly there. Certainly you can feel many ways about it. I think the idea that the laws of physics disagree with our basic intuitions in sort of fundamental ways is not really a new idea. That idea. The idea probably goes back, at least to Newton. Nowadays, most people probably, I don't know what most people are like, but it's sort of easy these days to think you have some intuition about, theory of gravity, meaning the classical Newtonian theory of gravity, where you have different bodies and they exert some pull on each other. And that kind of makes sense, but that was an extremely uncomfortable idea, even for Newton.
Yeah, but it influenced history. I find it strange that you're blasé about this, because like if you look at Newtonian physics, they influenced history and they influenced intellectual thought and mainstream thought in profound ways that we still experience today. Like
influenced religion.
Yeah, like modernism.
Influenced like the way that people interpret the meaning of life.
Yeah, exactly. Like Newtonian physics is deeply tied in with modernist thought, and now we have quantum physics, and it's tied in with postmodernist thought and tied in with all these other forms of thought that are dominant now in society. Like we're having like a major philosophical paradigm change in society, and it's deeply woven in with quantum physics.
Well, I think, to the extent that these sorts of societal changes in the way things are thought about have been going on, I think, I don't think they're really due to the some discovery about what the laws of physics actually are. I think they're due to these sort of new conceptions about the way that things, the way that things can possibly be. You know, the way that societies behave, the way that people behave, the day-to-day experience of life, like that has not changed as a result of the discovery of quantum mechanics. You know, like
it has changed enormously. Okay, look at Newtonian physics. Like if you look at like discoveries in Newtonian physics, he like basically demonstrated that the world around us functions like a machine that can be observed and predicted. And if you take the objects around you and you apply the right kind of math to them, you can predict them with extreme accuracy, and everything around you works like this magnificent clockwork, and that everything is connected in this cause and effect comprehensible way. That was a massive paradigm shift in society, and it affected the way that we think about ourselves. It affected the way that we educate children. It affected the way that we do medicine. It affected the way that we philosophize. Like if you look at 400 years of philosophy, like
yeah, I see.
It's modernism. Modernism has massively influenced society. It's built the buildings around us, and now there's this new kind of physics that's much newer. So its effects are in their infancy compared to the effects of Newtonian physics, but they're already having a massive impact on the way people think, on the way people choose to live their lives. And it's a feedback loop. It's not just that the physics affects society, but like they feed into each other.
Yeah, I mean, you're right. I mean, such things happen. I guess what I'm trying to say is that, you know, the laws of physics haven't changed during this time.
Right. The physical world that we're living in is still operating under the same laws as it was before. At least we assume. But I think that's a pretty fair assumption. Right.
You know, we were quantum beings, you know, based on the rules of quantum mechanics, you know, even at the time of Newton.
But it's kind of like something like quantum physics is kind of like, okay, imagine this would be a physical discovery, a scientific discovery. We discover that there's like, okay, imagine we discover that we're living in a simulation and there's a puppet master directing every way that we go. That would probably have big implications for how people live our lives and how people feel about everything. And I think that something like quantum physics, we don't really understand it so much, but something like discovering that reality is probabilistic, maybe, or the more we learn about it, the weirder it's going to get. I think it's going to have massive effects. It already makes me personally uncomfortable. Not that I was sitting super comfortably before, but it's, you know, it's something. Does it hit you?
Well, you know, it's a mathematical theory that predicts everything that we've already observed. You know, it doesn't, you know, from my perspective, nothing operationally has changed. It's not like I've learned about quantum mechanics and now, you know, when I walk out my door in the morning, I'm like, well, maybe the sun won't be there and that'll be interesting.
Right. Like, well, no, but it's changed our level of knowledge. Like, you know, if I was, let's say, an educated person in the 1700s and I walked outside my door and I looked at the sun rising in the sky and someone riding by on their, I don't know if they had bicycles, but let's say it was the 1800s and they ride by on their bicycle and the building is standing and it's bricks, and I'm looking at that and I'm seeing a Newtonian world. Like my level of knowledge, I'm like, it's all a great clockwork. The universe is one great machine where the process of cause and effect. And, you know, that's the way I'm seeing it. That's my level of knowledge. But now if I look out the door and I see the bicycle go by and I see the sun rising, well, the sun is complicated. Let's say I see the bicycle by and I see the building standing and I see the ball rolling down the hill. I look at all that and I'm saying, like, they're all displaying classical behavior, but I know that they're only doing that because I happen to be sitting in this very specific corner of reality at this very specific size, and that if I go smaller, then everything becomes extremely weird.
Yeah, maybe everything's just some kind of a construction.
Well, yeah, but I think a lot of that is that, you know, we evolved to exist in this, you know, at this level of size and this level of time and this scale, you know, and so we're used to dealing with it, and so it makes sense to us. And when we try to zoom way out, we get general relativity, and we try to zoom in, we get quantum mechanics, and those are both kind of paradigms that people find very unintuitive because we don't exist, on those, massive time scales or tiny size scales. But yeah.
Not just unintuitive, but also it has some weird implications for things like free will. It has some weird implications for things like life and death. Okay, if you took the many worlds interpretation, is there a reality where you're still alive? Is every I don't know. Is everything possible that we can imagine, or are there still certain constrictions? Is it just that some things are extremely unlikely, but there's still like one or two universes where Abraham Lincoln is alive today?
Yeah, or like if you almost get hit by a car or something, or you do something really risky, does it mean that like you lose a whole bunch of views, even if you survive?
You have to sort of believe that all of these events are somehow deriving from quantum superpositions, and that idea.
Well, it's an interpretation. It's an interpretation. We're speaking speculatively. I think we understand that.
Sure. I think in some situations it's like quite clear that there are no quantum superpositions involved, and in other situations it's maybe not so clear.
Yeah, I understand that it's not clear for classically sized phenomenon whether we're causing wave function collapses by our everyday actions. I think we all understand that, but we're speaking speculatively.
And it probably seems unlikely that that's the case. But
yeah,
I don't think it seems unlikely, though. It seems like they have observed quantum phenomenon for classically sized objects.
Yeah, but like John said, you had to work really, really, really hard to keep it in a super state.
Well, but then, I have to bring up Schrodinger's cat now. Like, you can set up a particle in a quantum superposition and do a measurement, which is a probabilistic measurement, and then, the sort of violent analogy or violent thought experiment that follows is that you either kill a cat or not, depending on what you measured. Mm-hmm. And now, if you want to, if you believe this all plays out according to many worlds interpretation, then there's a term in the wave function where you did kill the cat, and there's a term in the wave function where you did not kill the cat.
And in the Copenhagen interpretation, the cat is both dead and alive at the same time until you look in the room.
Well, so then if you want to say there is collapse of the wave function, then we have to talk about where the collapse occurs. Yes, sort of the original point of the thought experiment is that if you isolate this cat and the machinery, now it's no longer you that's killing the cat, it's some machine that's killing the cat, or not killing the cat. But if you isolate that from everything else, then you have to sort of believe, according to the rules of quantum mechanics, that the cat still exists in the superposition until you interact with it.
Yeah, until you observe it.
Or you have to believe that there's something else causing the collapse of the wave function. Maybe wave functions just collapse when they get larger than your thumb or something. That would be kind of ridiculous, and no one believes that. But
So I have just a really simple question for you, John.
Mm-hmm.
Do you believe in objective truth?
I think the question is too simple for me to give a meaningful answer. I don't know what you're really asking there.
Well, are there certain things that are objectively true? Like, does reality exist out there, or are we just like, could we be brains in a vat, or could we be in the Matrix or in a simulation? Go for it.
Well, there's maybe a couple different things you brought up there, but could we be in a simulation? Sure, but so long as the rules of the simulation continue to be followed, there's no sort of meaning to that. If there's no way to get out of the simulation, then we may as well not be in a simulation. There's just nothing else. So there's sort of nothing to say about that. Now, if you're saying, we're in a simulation and there was a puppet master brought up earlier, and if we somehow discover the puppet master, then, well, it turns out, we were not in this perfect simulation. There was a way out of the simulation, and now we actually exist in this more complicated universe, and we have to rethink things.
Going back to Schrodinger's cat, if you actually set up that experiment correctly, to me, the interpretation that the cat is both dead and alive at the same time seems really unintuitive and really, really unreasonable, much more unreasonable than the many worlds interpretation. Is this idea that you could actually have a cat itself in a superposition commonly accepted, or how do you feel about it?
I don't, well, I don't want to speak for everybody. I don't know if I want to say that it's commonly accepted. I think, it's a thought experiment designed to get at exactly what's uncomfortable. But I do think that it's no more uncomfortable in the many worlds interpretation. If you believe that you can exist in the wave function in two different states, in two different places in the wave function, then there's no fundamental difference between that and a cat existing as a live cat in one place in the wave function and a dead cat in another place in the wave function. And then
they're both.
we perhaps want to ask, well, could I exist in the wave function as a live me and a dead me? And that's even more uncomfortable.
I mean, if a cat could, then you certainly could, right? We just swap out you for the cat in the experiment.
There's nothing fundamental preventing that. Yep.
Just ethics. Like, I mean, animal experiments, people seem to be more comfortable with. I don't know if anybody's ever going to set this up, but if they did, people seem to really like messing with cats, so they'd probably do it with a cat.
They still can't know, because once you've observed whether the cat's alive or dead,
Right,
once you know, like you can't observe the cat prior to observing it and collapsing the wave function.
Yeah, and I guess the observer appearing two times in the equation brings up the possibility that, well, I guess we kind of already said this, but like that you're in a superposition of two different states, as viewed from outside. Like, so yeah, like we could put a scientist into the room with the cat, and the scientist opens the box and observes whether the cat is alive or dead, and if you still haven't, talked to the scientist about what he observed, then essentially the scientist and the whole system with the cat is still in a superposition of states. And so it almost seems like there's these different realities that people can exist in when they haven't communicated with each other.
Yeah, it's all just the laws of quantum mechanics.
Yeah, that's an interesting one. Like the idea that like it flows outwards. Isn't that kind of like decoherence, like the idea of decoherence?
Yeah, so decoherence is another word that comes up a lot in this subject that we've sort of tangentially touched on, but not by name. But sort of as I was saying earlier, like would you do an experiment where you put some particle in a quantum superposition, you have to be a little careful about it. Well, maybe you have to be a lot careful about it. You have to preserve that superposition by making sure that the particle doesn't interact with something that would sort of in effect cause measurement, which is essentially what people call decoherence, where you have set up the wave function in some superposition state, and then it interacts with the environment, and as it interacts with the environment, very quickly that state becomes a superposition, without bringing wave function collapse into this, that state becomes a superposition of these very large states that involve very many things, and it's no longer, the reason it's sort of called decoherence is because it's no longer possible for those two different states of the particle to interfere, because they're sort of tangled up with the states of all the things around them. And in order for two states to interfere, they have to really be, states of just that one particle that you want to interfere.
Yeah, this language of entanglement makes me think that all of these particles are like tied together with balls of yarn or something.
Oh no. Well, it seems like it's kind of more what you just described, Chris. Like one way to interpret it could be like that, is if it's like you have like the box and the cat and the scientist, like they're kind of now. I don't know if this would be a way to. I don't know if I'm totally stretching here, but like that's almost like a kind of entanglement. And then once you observe it, then you're also entangled with them, and it's like a chain reaction outwards. I don't know if I'm totally butchering those concepts, but that's what it makes me think of.
Yeah, I mean, I think the thing that causes the information to propagate is sort of repeated measurements. So the scientist measures the cat, and then the other scientist measures that scientist, and then the information of what was observed kind of propagates out. But each time that happens, it's because there's been a new measurement that's occurred.
Yeah, that's one way of looking at it, but we don't really know, I guess, because
and it would be impossible for us to know by the setup itself.
Yeah.
I mean, there is, when you ask this question of like, when does a measurement occur? You can try and answer that question with a bit more precision than we've explained so far, and that's sort of what this subject of decoherence that's been brought up. That's sort of the question that subject asks is, how much does this quantum superposition have to interact with its environment or things around it, so that it's no longer possible to recover these interference effects. So you can do a bunch of math and work out when you think that happens, and then you can say then you can bring interpretation back into this and say, well, maybe at the point where decoherence has taken place, some kind of collapse of the wave function also has to take place. Or you can say, well, I still believe in the many worlds interpretation, and all these possibilities are still there, but it's no longer possible to speak of all of them at once and recover interference effects because things have decohered.
I feel like I'd be maybe interested in talking a little bit more about what it all means. Like, I know we've been talking about that a lot, over and over, but yeah, I don't know. Maybe if we can just like tune down a little bit our critical voice, or our like trying not to stretch outside the science voice, and maybe tune up our speculative voice. Maybe we could have a 10-minute speculation session where we just speculate about what it all could mean.
I'd be down for that.
Okay.
Chris, we were proposing to wrap up with tuning down our critical voices and tuning up our speculation voices, and having kind of a speculation session about what it all means.
Oh, that's what I've been doing the whole time. But yeah, let's do it.
So obviously ghosts.
I like it.
What do you...
Actually, DMT people talk about spirits. So maybe it's that.
So it's difficult to say. Like, I don't know if this randomness or this quantum weirdness would imply ghosts or spirits, or if to me it wouldn't make any sense, and it wouldn't make any more sense if we brought spirits into it. It would just add another layer of spookiness, which wouldn't make the results we're getting from quantum physics like any more coherent or make sense to me more.
Sorry, I was joking.
Yeah,
I know. I know you were joking about ghosts, but I know you were joking about ghosts, but like a lot of people do want to bring spirituality into this. Like a lot of people are inclined to say like that the non-causality that we seem to see at the quantum level is proof of God, or like a spirit realm or something like that. I know a lot of physicists don't want to say that, but like a lot of everyday people.
Well, I mean, so traditionally, God has been used to explain all the stuff that we don't understand, and quantum mechanics basically proves that there's all this stuff that we fundamentally can't understand. And so, if you if you want to call that God, then I guess a lot of people do that.
And basically, like, I get the argument about like God in the gaps, and we don't just want to invoke God reality for things we don't understand. But we look at something like quantum physics, it does seem to at least suggest the possibility that our conscious minds play a big role in the actual composition of physical reality. It's that physical reality responds to our conscious minds in really unexplained and unintuitive ways, or at least ways that are unintuitive according to like the Newtonian view of reality that we all still tend to be raised with. And I mean that just it seems to elevate the importance of the mind, and God is, it's the idea that of a cosmic mind. So I see the association. I'm not saying it's proof, but I don't think it's crazy to say there's an association there.
So I'm inclined to not want to invoke the mind whenever I read about quantum physics or hear about quantum physics, and I was kind of hoping that maybe this conversation would help me understand a little bit more. But it really is difficult when physicists always invoke an observer. It's like the language that's being used implies a mind that's doing the observing, and then when I ask about it and how it doesn't have to do with an observer itself, like things get kind of shaky. And then you do read some physicists say that it does have to do with an observer, or maybe consciousness does have something to do with it. I really don't know. I want to just rule out consciousness having anything to do with anything completely, but these conversations do make it difficult.
Yes. So let's see. I mean, so first of all, philosophically, without even bringing up quantum mechanics, if you want to understand your reality, well, you are a mind. So there's some necessary sense in which the mind must play some big role in that. It's certainly true that there are lots of people who involve consciousness in the operation of quantum mechanics, and that's always in exactly this sort of consciousness causes collapse way, where you look at this wave function that has many versions of you, and you say, well, this is fundamentally uncomfortable because there shouldn't be many versions of a conscious being, and so the thing that causes the collapse must be the fact that conscious beings can only have one term in the wave function. And I don't think there's anything fundamentally, I don't think that's a great argument. I don't think there's any, physically there's nothing special about consciousness that makes any difference there. It's merely
you don't know that. Like the measurement problem is unresolved. Like it's not just that we're being, it's not just that we're ignorant. The measurement problem is a legit problem in quantum physics, is they don't actually know what part of the process of taking a measurement causes the wave function collapse or not. Okay, that's one of causes the observed particle-like behavior to occur.
I would clarify that and say that the measurement problem is an unresolved problem in quantum philosophy. If you look at any of the usual interpretations of quantum mechanics, they all make the same predictions. You can pick whichever one you want. So there's no, from the physics perspective, there's no problem of, well, I did this experiment, but now I have to think about when the measurements actually occur. I mean, you have to think about when the measurements actually occurred, but that there's physical meaning there. You don't have to think about, well, which conscious observers were involved in this experiment, and so what should I actually predict? The results are just determined by the equations of the physics.
Our equations give us good predictions regardless of how we interpret what's actually going on, but many people are interested in what's actually going on, not just what the math predicts.
Right, and to the extent that it continues to be true that the laws of quantum mechanics continue to hold, we don't find any way in which they're violated, and to the extent that that continues to be true, there's a sense in which you can be agnostic to the interpretation that you want to choose. All the interpretations make the same predictions, so how can you say that one is better than any other?
Right.
Now,
but all of the predictions are really wonky. Or not all of the predictions. All of the interpretations are really wonky, whichever one you choose.
Right. You certainly have to contend with the fundamental things we've learned about the nature of reality through the laws of quantum mechanics, which are not classical laws. They don't obey our classical intuitions.
Do you think that there will ever be an interpretation of quantum mechanics that is coherent and understandable by like the average person?
Uh, I'm very hesitant to make statements about the average person. I'm not sure. I'm not sure I know who the average person is.
All right. Well, but
I mean-
but to you, I mean, all of the interpretations of quantum mechanics are pretty weird, right? And hard to wrap your head around. I mean, I guess you've kind of spent a lot of time doing the math, obviously, and you know, yeah, seeing how to predict events. But you know, when I asked you what's your favorite interpretation of quantum mechanics, it seems like you're mostly just picturing what the math is doing, and you're not really picturing what the things are doing. And like, do you think there ever will be an explanation of what the things are doing?
I guess I would take issue with drawing a distinction between what the math is doing and what the things are doing.
Well, but clearly one is making predictions. The math is being used to make predictions, and the model is just, you know, well, just pick your interpretation. You know, so one, I mean, in classical mechanics, there's definite explanations for what objects are doing and how forces are acting on things. And, you know, there's only one interpretation of classical mechanics, right? Whereas, you know, in quantum mechanics, there's all of these different possible interpretations. I guess maybe my question should be, do you think there will ever be just one interpretation of quantum mechanics that's the best interpretation?
Do I think there will ever be? Well, I don't think I have a definitive prediction to that. I think it's sort of believable that the laws of quantum mechanics will continue to hold in the way that you know, they normally do, and that, in some sense, will always leave this question open. Now, it's certainly possible that we discover some new physics which changes things. You know, in particular, sort of the most fundamental way to test the ability of quantum mechanics to really do what quantum mechanics does is to build a scalable quantum computer. And we have not done that. There's no fundamental reason we know of that we should not be able to do that. And of course, there are many ongoing efforts to do so. But I think if such a thing can be built, then that pretty convincingly shows us that the laws of quantum mechanics continue to hold, and, you know, whatever discomfort I have with this sort of exponential blowup, I'll just have to deal with. On the other hand, if we find that there's some kind of fundamental difficulty there, and that would have to be new physics. But if we find new physics, then, you know, that, of course, will change everything.
Okay, I think we're at a good point to wrap up. Does anyone have any final comments?
Whenever I talk about quantum physics, I always come out feeling like I've learned something very interesting, which just left me with a whole bunch more questions. And I still haven't integrated it into my life in terms of how I feel that this information affects reality, or how I should be operating in the world. And, you know, maybe I should just go on without trying to do that. But that integration process is something that's generally pretty important to me and seems extremely difficult to do with quantum physics. So I'm curious to see what new physics we might get in the future.
Yeah, I would agree with that. I also find it very challenging to integrate quantum physics. I would definitely affirm the importance of trying to understand the philosophical implications of quantum physics as a specific point of a more general argument that philosophy is extremely important in how we live our lives, how we interact with reality, how we shape the course of history. And so I think I don't see that philosophy has fully integrated the findings of quantum physics either. Such a journey for all of us.
Well, thank you, John, for coming on. This is really interesting and challenging and awesome.
Yeah, thank you so much. So thanks everyone for coming on this journey with us. It's been really interesting, and I think we've all learned a lot about physics. So thank you and goodbye.
Adios. Thank you for joining us on the Multiversity. We hope you found this episode both mind-bending and enjoyable.
We can be found all over the social media space and at multiversitypodcast.com.
If you like this content, give us a like, comment, follow, share, or support us on Patreon.
Catch you on the flip side.